Tonight, I want to tell you about a world you will never see with your own eyes, that you will never visit, that perhaps no one will ever visit. A world 500 light-years away, in the constellation Cygnus, the Swan. A world that, when it was discovered in 2014, captured our imagination like no other exoplanet before. Kepler-186f, the first Earth-sized planet found in the habitable zone of another star. The first world where liquid water, and therefore, potentially, life, seemed genuinely possible. Not a gas giant like Jupiter, not a massive super-Earth, but a rocky planet. The right size, in the right place, a possible second Earth. And since its discovery a decade ago, Kepler-186f has been the focus of dreams, of speculation, of hope. Artists have painted it with blue oceans, green continents, thick atmospheres. Scientists have modeled its climate, its potential atmosphere, its seasons. Writers have populated it with alien ecosystems, with life, with civilizations. It is the exoplanet of our dreams, the leading candidate for life beyond Earth. But tonight, I want to give you the truth about Kepler-186f. Not the fantasy, not the unfounded hope, but what we really know, and what we don't know. The reasons why it is promising, and the reasons why it could be completely dead. The challenges it faces, the massive uncertainties surrounding every aspect of this distant world, because after a decade of study, of modeling, of observation, we have learned something humbling. Kepler-186f is a mystery, profound, almost impenetrable. At 500 light-years away, it is too far to study in detail. We can't see its atmosphere, we can't measure its precise mass, we can't photograph it directly. Everything we know comes from inferences, from models, from educated guesses, and those guesses could be wrong. Tonight, for the next 2 hours, I want to take you on a deep dive through everything we know about Kepler-186f, its discovery, its host star, its orbit, its size, the challenges it faces, the radiation, the likely tidal locking, the atmospheric uncertainty, and the reasons why, despite all this, it remains our best candidate, or at least one of them. In the end, I won't give you a simple answer, because there isn't one. Kepler-186f could be paradise, oceans under a red sky, life thriving in conditions we can barely imagine, or it could be a barren rock, no air, no water, completely dead. We don't know, and we won't know, maybe for decades. But what we do know is enough to paint a picture, a complex picture, fascinating, full of possibilities and uncertainties, of a world on the edge between life and death, between hope and disappointment. So let's begin with April 2014 and the announcement that changed how we see our place in the universe. Chapter 1. The Discovery. April 2014, Earth's first cousin. On April 17, 2014, NASA called a press conference, and the title was intriguing: Kepler Exoplanet Discovery. Rumors had been circulating, something important, something about a planet the size of Earth. And when the announcement came, it delivered on the promise. A planet, Kepler-186f, the fifth planet in the Kepler-186 system, with a radius approximately 1.1 times that of Earth, orbiting in the habitable zone of its star, where liquid water could exist. The first Earth-sized planet in the habitable zone of another star. Not a massive super-Earth which could be gaseous. Not a gas giant like Jupiter, obviously uninhabitable, but a rocky planet, the right size, in the right place, a cousin of Earth. The discovery was made by the Kepler Space Telescope, launched in 2009 with one mission to find Earth-sized planets around other stars. Using the transit method, continuously observing thousands of stars, looking for periodic dips in brightness, caused by planets passing in front of their stars. And Kepler was extraordinarily successful. During its primary mission, before its reaction wheels failed in 2013, it discovered thousands of exoplanet candidates. Hundreds were confirmed, transforming our understanding of how common planets are. But Kepler-186f was special because it wasn't just another exoplanet, it was an Earth-sized planet in the habitable zone, the combination we had been looking for. The data showed Kepler-186f transits its star every 129.9 days, blocking approximately 0.0015% of the star's light during transit. From that transit depth, scientists calculated the size of the planet, approximately 1.11 times the radius of Earth, and from its orbital period and the star's luminosity, they calculated its orbital distance, approximately 0.356 astronomical units, about 1/3 of the distance between Earth and the Sun. But because the star is much dimmer than the Sun, Kepler-186f receives about 1/3 of the light that Earth receives, comparable to Mars, but still within the habitable zone. And the scientific world exploded, because this was the moment we had been waiting for. Planet like Earth, orbiting in the habitable zone, potentially habitable, the first real candidate for a second Earth. The media called it Earth's cousin, Earth's twin, and people dreamed of oceans, of life, of possibilities. But even then, scientists warned, that habitable zone does not mean habitable. That we still knew nothing about its atmosphere, its composition, its history, that it could be a dead world, like Mars, like Venus. But the warnings were drowned out by excitement, by hope, by the dream that maybe we are not alone. Chapter 2. The host star, Kepler-186, the red dwarf. To understand Kepler-186f, you first need to understand its star, Kepler-186, a red dwarf, an M-dwarf. The most common type of star in the galaxy, approximately 70% of all stars, but very different from our Sun. Kepler-186 has approximately 48% of the Sun's mass, and approximately 52% of its diameter, larger than Proxima Centauri, but much smaller than the Sun. And it's dim, incredibly dim. Luminosity of about 4% of the Sun in visible light, 25 times less bright. You couldn't see it with the naked eye from Earth. Even if it were as close as Alpha Centauri, you would need a telescope. And it is cold. The surface temperature is approximately 3,800 Kelvin, compared to approximately 5,778 Kelvin for the Sun. So it glows with a red-orange glow, and it emits most of its light in infrared, not in visible light. And it lives a long time. The Sun will live for about 10 billion years. Kepler-186 will live for trillions, because it fuses hydrogen very slowly, conservatively. It's a candle that will burn for eons. And here's the critical thing. Kepler-186 is relatively quiet, not as violent as Proxima Centauri, not as prone to massive eruptions. It still has stellar activity, all M-dwarfs do, but it's moderate, manageable, not catastrophic. And that's important, because stellar flares are one of the biggest challenges to habitability around red dwarfs. Flares that can strip away atmospheres, sterilize surfaces, kill life. But Kepler-186 appears to be relatively benign, not safe, but not extremely dangerous. And it has planets, at least 5 that we know of. Kepler-186, B, C, D, E, and F. The 4 inner ones orbit very close, too hot for liquid water. But the fifth, Kepler-186f, orbits farther out, in the habitable zone, where the temperature could be just right. Chapter 3. Size and Mass. What kind of world is it? We know that Kepler-186f is about 1.11 times the radius of Earth. That's from transit, from how much starlight it blocks. But what about its mass? Here's the problem. We can't measure Kepler-186f's mass directly. At 500 light-years away, it's too far for the radial velocity method. That method requires measuring the wobble of the star caused by the planet. And at 500 light-years, the wobble is too small. The planet too light, the signal too weak. So the mass is an estimate, based on models. If Kepler-186f is rocky, like Earth with a similar composition, then its mass should be about 1.4 to 1.7 times the mass of Earth, because mass scales roughly with the cube of the radius, for rocky planets. But that assumes it's rocky. What if it's more like a mini Neptune, with a rocky core but a thick atmosphere of hydrogen? Then it could be more massive, 2 to 3 times the mass of Earth, with much higher surface gravity and very different conditions. Or what if it's mostly ice, like a large Galilean moon? Then it could be less massive, about Earth's mass, or even less, with Earth-like surface gravity. But completely different composition, so we don't know. The mass is uncertain, and that matters, because mass determines gravity and the ability to retain atmosphere. And composition determines what kind of world it is, rocky like Earth, or something completely different, but based on size, 1.11 Earth radii. Most models suggest that Kepler-186f is probably rocky. Planets smaller than about 1.5 Earth radii tend to be rocky. Larger planets tend to be mini Neptunes, with thick atmospheres of hydrogen. So probably, Kepler-186f is rocky, with a solid surface, potentially habitable, but we don't know for sure, and we won't know until we can measure its mass directly, which may not happen anytime soon, given the distance. Chapter 4. The Habitable Zone. How habitable is it really? Kepler-186f orbits in the habitable zone of its star. That means it gets the right amount of starlight for liquid water, if it has an atmosphere, if it has water, if the conditions are right. But habitable zone is a broad concept. With fuzzy edges, it's not a precise ring, but a region, with an inner edge and an outer edge. The inner edge is where it's too hot, where the greenhouse effect runs wild, and water boils, like Venus, which is just inside the inner edge of the Sun's habitable zone. The outer edge is where it's too cold, where even with a thick CO2 atmosphere, water freezes, like Mars, which is just outside the outer edge, or on the border, and Kepler-186f is on the outer edge, not in the middle, where conditions are most favorable, but on the edge, where it's cold, where liquid water is barely possible. It receives about 1/3 of the light that Earth receives from the Sun, comparable to Mars, and Mars, as we know, is cold, very cold. Average temperature of about -63 degrees Celsius. So if Kepler-186f has a thin atmosphere like Mars, it would be frozen, too cold for liquid water on the surface. But if it has a thick atmosphere, rich in greenhouse gases like CO2, then it could trap enough heat to allow liquid water. And here's the problem. We don't know what kind of atmosphere it has, or if it has any atmosphere at all. It could have a thick atmosphere or a thin one, or none at all. We don't know, and that determines everything. Without an atmosphere, Kepler-186f is frozen, barren, dead. With a thick atmosphere, it could be temperate, habitable, possibly alive. So, in the habitable zone, is promising. But it's not a guarantee. It's not proof of habitability. It's simply a possibility, a hope that with the right conditions, atmosphere, water, chemistry, Kepler-186f could have liquid oceans. And where there are oceans, there could be life. Chapter 5. The problem of tidal locking. One side always day, one always night. And now, a major complication. Kepler-186f orbits very close to its star, every 129.9 days, at only 0.356 astronomical units, about 1/3 of the Earth-Sun distance. And at that distance, tidal forces are significant. The star's gravity pulls harder on the near side of the planet than on the far side. And over time, over millions or billions of years, those forces synchronize the planet's rotation with its orbit. Tidal locking, like our moon, which always shows the same face to Earth. Kepler-186 probably always shows the same face to Kepler-186. One hemisphere, the day side, constantly facing the star, perpetual light. The other, hemisphere, the night side, constantly facing space, perpetual darkness. And that has massive consequences. On the day side, the star never sets. It hangs in the sky, always in the same place, shining continuously. A red-orange sun, weak compared to our sun, but constant, and with no rotation to distribute the heat. The substellar point directly under the star could get hot, while distant regions remain cooler. On the night side, the star never rises. It is perpetual darkness, illuminated only by distant stars, and with no starlight to warm it. The night side freezes, deeply, all the water freezing, carbon dioxide snow falling, and if there's no atmosphere to transport heat, then you get massive extremes. The day side potentially warm in the center, but frozen at the edges. Night side completely frozen, maybe minus 100 degrees Celsius or colder. But if there is an atmosphere thick enough, then everything changes. The atmosphere transports heat through winds, circulation. Warm air on the day side rises, flows to the night side, cools, descends, creating a global circulation pattern. And if the atmosphere is thick enough, it can moderate temperatures, making the entire planet, both sides, have habitable temperatures, or at least creating a habitable band around the terminator. The line between day and night. Perpetual twilight, where temperatures are moderate, neither too hot nor too cold. Climate models of tidally locked planets show this. With a thick atmosphere, you can have liquid water globally, or in the twilight zone. Without an atmosphere, the planet is extreme, inhospitable. So again, it all depends on the atmosphere, which we don't know if it exists. Chapter 6. The red light. Photosynthesis under a different sun. And now something that is often overlooked. Kepler-186 is a red dwarf. It emits mainly red and infrared light, not white light like the sun, not blue-green light, but red and weaker. And that has implications for potential life. Because on Earth, photosynthesis, the process that drives almost all life, uses visible light, mainly blue and red, reflecting green. Plants are green because they reflect green light. They absorb blue and red. But on Kepler-186f, there is much less blue light. Most of the light is red and infrared. So if there is photosynthetic life there, it would have to adapt, use mainly red light and infrared. And that's possible. On Earth, there are bacteria that do infrared photosynthesis, using bacteriochlorophyll instead of chlorophyll. So life can adapt, use different wavelengths, but it would change the color of plants. Instead of green, they could be black to absorb all the available light, or red, or purple, reflecting what they don't use. So an inhabited planet around Kepler-186 might not look like Earth. Blue oceans, yes, if there are oceans, but land covered not with green forests, but with black forests, or red, or purple, alien, strange, beautiful in its own way. And the sky would be different. With an Earth-like atmosphere, the sky would be, well, it depends. It could be blue, if there is Rayleigh scattering, or it could be more orange-reddish, if the dust particles scatter differently. We don't know. But the Sun, Kepler-186, would be red-orange, larger in appearance than our Sun, because even though the star is smaller, it is closer, approximately 2 to 3 times the angular diameter of our Sun as seen from Earth. A large disk, red-orange, hanging in the sky, and the light would be dimmer, warmer in colour, like perpetual sunset. On the day side, beautiful, but strange, to eyes accustomed to sunlight. Chapter 7. Radiation and Eruptions. Is it safe? Now the problem of radiation, because all red dwarfs have stellar activity, star spots, magnetic fields, and flares. Kepler-186 is relatively quiet, compared to stars like Proxima Centauri, but it still has flares, regularly, not as massive, not as frequent, but present. And every flare releases radiation, X-rays, ultraviolet charged particles, bathing the planets in its habitable zone. For Kepler-186f, orbiting at 0.356 astronomical units. That radiation is significant, not as extreme as Proxima b, but higher than Earth. Probably 10 to 50 times more X-rays than Earth. And during flares, much more. Can life survive that? It depends. If there is a thick atmosphere, it absorbs a lot of radiation. It protects the surface. And if there is a magnetic field, it deflects charged particles. So with the right protections, life is possible. But without an atmosphere or magnetic field, the surface would be irradiated, hostile to life. Broken organic molecules, damaged DNA, sterilization. And here's the critical question. Does Kepler-186f have a magnetic field? We don't know. We can't measure it from here, but it depends on having a molten core, rotating, convecting. With 1.11 Earth radii and an estimated mass of 1.4 to 1.7 Earth masses. Kepler-186f probably has a substantial iron core. And if that core is still molten, if it's still hot enough, then it could generate a magnetic field. But tidal locking complicates things. Slow rotation, once every 130 days, could weaken the dynamo. Or tidal forces could help, heating the interior, driving convection. We don't know, so radiation is a concern, but not an absolute obstacle. With an atmosphere and magnetic field, Kepler-186f could be protected. Without them, it's probably barren. Again, it all depends on things we don't know. Chapter 8. The Search for Atmosphere. How can we detect it? So the most critical question about Kepler-186f is, does it have an atmosphere? And if so, how thick is it? What is its composition? We can't answer that right now. Kepler-186f is too far away, 500 light-years, and its star is too dim, and the planet too small. We can't do transmission spectroscopy. We can't measure thermal emission. The signals are too weak, with current technology. But future missions could try. The Habitable Worlds Observatory, HWO. Proposed by NASA for the 2030s or 2040s. A space telescope designed specifically to study habitable exoplanets. With coronagraphs to block starlight, revealing faint planets, and spectrometers to analyze atmospheres. HWO could, in theory, detect the atmosphere of Kepler-186f. Measure its composition. Look for oxygen, methane, water vapor. biosignatures. But it's difficult, even for HWO. Kepler-186f is at the limit of detectability. It could take years of observation time to obtain a usable spectrum. And there are easier targets, closer planets, around brighter stars. So Kepler-186f might not be a priority. We could study Proxima b first, or TRAPPIST-1e, or LHS 1140b. Planets that are closer, easier to observe, so we may not know about the atmosphere of Kepler-186f for decades, perhaps for our entire lifetime. It's an open question, waiting for future technology. Chapter 9. The Planet Brothers, a system of 5 worlds. But Kepler-186f is not alone. It has siblings, at least 4 that we know of. Kepler-186b, C, D, and E. All orbit much closer to the star than Kepler-186f. Kepler-186b, 3.9-day period. Very hot. Probably molten rock. Kepler-186c, 7.3-day period, also very hot. Kepler-186d, 13.3-day period. Hot. Perhaps thick atmosphere. Kepler-186e, 22.4-day period. Still hot. Inner edge of the habitable zone, and then Kepler-186f, 129.9-day period. In the habitable zone, the outer planet, the cold one, the promising one. And there could be more planets that we haven't detected. Smaller planets, or planets with longer orbits, or planets that don't transit from our perspective. But of those we know, Kepler-186f is the only one in the habitable zone, the only one where liquid water is possible. The others are too hot, too close. Could there be life on the inner planets? Probably not. Too hot for liquid water on the surface. But maybe subsurface life, in underground oceans, if they exist. Or maybe life in the upper atmospheres, on planets with thick atmospheres. It's speculative, but possible. But Kepler-186f is the leading candidate, the world where surface habitability is most plausible, the world where we dream of finding oceans, continents, life. Chapter 10. Comparisons. Kepler-186f versus other exoplanets. So how does Kepler-186f compare to other habitable exoplanets? There are thousands of known exoplanets, hundreds in habitable zones, but only a few are Earth-sized and in habitable zones, around quiet stars. Proxima Centauri b, closest. Only 4.24 light-years away, but it orbits a very violent star. TRAPPIST-1e, Earth-sized, in the habitable zone, but around an ultra-cool dwarf, and probably tidally locked. LHS 1140b, more massive, super-Earth, but in the habitable zone of a quiet red dwarf. Teegarden star B and C, Earth-sized, in habitable zones, around a very faint red dwarf. And Kepler-186f, not the closest, but not the farthest either. Not around the quietest star, but not the most violent either. Not the most Earth-like planet, but close. It's a good candidate, among many. Not necessarily the best, but promising. And here's the thing. All these planets are mysteries. Proxima b may have lost its atmosphere. TRAPPIST-1e may be frozen. LHS 1140b could be a world of water with no land. And Kepler-186f could be completely dead. We don't know. But by studying them, all of them, we learn. About what makes a planet habitable, what makes it barren, about the diversity of worlds, the possibilities. And Kepler-186f, being one of the first discovered, it's iconic, symbolic. The first Earth-sized planet in the habitable zone, the one that started the dream. Epilogue. Living with uncertainty. So there you have it, everything we know about Kepler-186f and everything we don't know. We know it's the right size, 1.11 Earth radii, probably rocky. We know it's in the habitable zone, where liquid water is possible. We know it orbits a relatively quiet red dwarf, not extremely violent. We know it's probably tidally locked. One side day, one side night. We don't know its exact mass. We don't know if it has an atmosphere, and if it does, how thick. We don't know if it has a magnetic field. We don't know if it has water, or oceans, or continents. We don't know if it has life. And that uncertainty is frustrating. We want answers. We want to know. Is Kepler-186f a second Earth? Or a dead world? But we can't know. Not yet. Maybe not for decades. And that's okay. Because uncertainty is where science lives. In the space between what we know and what we don't know. In the questions waiting for answers. Kepler-186f is one of those questions. A world 500 light-years away. Too far to visit, too faint to study easily, but promising enough to dream about. And in the coming decades we will learn more, with better telescopes, better techniques. Eventually, we will detect its atmosphere, or confirm that it has none. We will search for biosignatures, oxygen, methane, signs of life. And, when we do, the universe will have changed. If we find life, even just evidence of a habitable atmosphere, we will prove that worlds like Earth are not unique, that life could be common throughout the galaxy. And if we find nothing, we will learn that habitability is rarer, more fragile than we expected, that Earth is special, precious, possibly unique. Either way, we will learn, and that is what makes it worthwhile. Good evening, sleep well, and dream of Kepler, 186f, 500 light-years away, orbiting under a red sun, with oceans, perhaps, with life, possibly, or just barren rock under an alien sky. We don't know. But someday we will. And on that day, everything will change. Good night.